The moment the power grid fails, modern civilization reveals how fragile it truly is. Lights vanish. Refrigerators fall silent. Water pumps stop pushing life through pipes buried beneath cities. Communication towers begin counting down the final minutes of battery backup before disappearing into silence. In those first uncertain hours, the difference between inconvenience and catastrophe becomes painfully clear. Electricity is not a luxury. It is the invisible bloodstream of survival. Without it, critical information disappears, medical equipment shuts down, navigation tools fail, and even the simplest devices that once seemed trivial suddenly become lifelines. In such conditions, people instinctively search for power anywhere it can be found, and one of the strangest yet scientifically valid emergency power sources hides in plain sight inside ordinary fruit. The lemon battery, often dismissed as a classroom curiosity, reveals a deeper lesson about chemistry, energy conversion, and the overlooked physics that govern survival when conventional systems collapse. The idea of producing electricity from lemons often triggers immediate skepticism. A small citrus fruit powering anything meaningful appears absurd in the context of modern energy systems capable of generating gigawatts across continents. Critics are quick to dismiss it as a novelty experiment rather than a survival tool. But this reaction misses the fundamental principle at work. Electricity does not require massive turbines, coal furnaces, or nuclear reactors. At its core, electricity is simply the movement of electrons caused by a chemical imbalance between two materials. The lemon itself is not the power source in the way most people imagine. Instead, the fruit functions as a chemical environment, a conductive electrolyte that enables a reaction between two different metals. In this sense, the lemon is not generating electricity at all. It is facilitating a process that humans have been using since the earliest days of electrochemistry. Understanding this process requires stepping back into the fundamental physics of how batteries function. Every battery on Earth, from the smallest watch battery to massive industrial storage systems, operates on the same underlying principle: the electrochemical potential difference between two materials. When two metals with different tendencies to lose electrons are placed in a conductive solution, a chemical reaction begins immediately. One metal begins releasing electrons more readily than the other. These free electrons attempt to move through any available conductive pathway toward the metal that holds onto them more tightly. If that pathway happens to be a wire connected to a device, electricity flows. Inside a lemon battery, the most common metal pair used is zinc and copper. Zinc acts as the anode, the metal that willingly gives up electrons. Copper functions as the cathode, the metal that receives them. The acidic juice of the lemon contains citric acid and dissolved ions, which create an electrolyte solution capable of transporting charged particles between the two metals. When zinc begins losing electrons in this acidic environment, those electrons travel through an external wire toward the copper electrode. At the same time, ions within the lemon's juice move internally to balance the charge difference created by this electron flow. The result is a small but measurable electrical current. This process may sound trivial, but its importance becomes clear when placed in the context of historical engineering. The lemon battery is essentially a simplified version of the voltaic pile, the first true battery invented in 1800 by Alessandro Volta. Volta's design used alternating discs of copper and zinc separated by saltwater-soaked materials, creating the first continuous electrical current ever produced by humans. That invention fundamentally changed science and engineering, allowing researchers to experiment with electricity in ways previously impossible. Electrochemistry, electroplating, early telegraph systems, and eventually modern batteries all trace their lineage back to this basic principle. The lemon battery is not a novelty. It is a demonstration of the same physics that powers nearly every portable electronic device in existence. Yet there is a persistent misunderstanding that limits how people perceive this technology. Many believe the fruit itself contains stored electrical energy waiting to be released, similar to a biological battery. This is not the case. The energy does not come from the lemon. It comes from the chemical potential of the metals inserted into it. The lemon merely provides the ionic pathway necessary for the reaction to occur. This distinction is critical because it reveals that lemons are not the only possible source of emergency electrolytes. Any acidic or conductive liquid, vinegar, salt water, certain plant juices, even soil moisture, can serve a similar function. The fruit simply happens to be convenient, widely available, and chemically effective. To understand the limits and possibilities of this system, we must examine the electrical output produced by a single lemon cell. A typical lemon battery generates roughly 0.7 to 1.0 volts depending on the metal pair and the acidity of the fruit. However, voltage alone does not determine usefulness. The current produced by a lemon cell is extremely small, usually measured in microamps to milliamps. This means the raw electrical power is tiny, far too small to run most devices directly. But this is where another often overlooked principle of electrical engineering becomes critical. Batteries can be connected in series and parallel to modify voltage and current. When multiple lemon cells are connected in series, their voltages add together. 3 lemons connected correctly may produce roughly 3 volts. 10 lemons might approach 9 volts under ideal conditions. Meanwhile, connecting multiple series chains in parallel increases current output. By scaling both voltage and current, even extremely small electrochemical cells can produce usable electrical energy. This is the same scaling principle used in massive battery installations supporting renewable power grids today. Evidence of the practical potential of fruit-based electrochemical cells appears repeatedly in educational experiments and emergency demonstrations. Researchers and hobbyists have successfully powered small LED lights, digital clocks, and low-power sensors using arrays of citrus batteries. The energy density is low and the efficiency is poor compared to commercial batteries. But the proof remains undeniable. Electricity can be generated anywhere 2 dissimilar metals and a conductive medium exist. For survival scenarios, this fact carries profound implications. Imagine a prolonged grid failure where conventional batteries have been depleted. Radios used to receive emergency broadcasts require small but consistent electrical input. Sensors monitoring water quality or environmental hazards often consume only tiny amounts of power. Even charging a capacitor slowly over time can accumulate enough energy to briefly power communication equipment. In these contexts, a primitive electrochemical cell becomes more than a curiosity. It becomes a bridge between complete technological darkness and limited operational capability. But there is another deeper layer of science, hidden beneath the simple lemon battery demonstration. The reaction occurring at the zinc electrode involves the oxidation of zinc atoms into zinc ions, releasing electrons into the external circuit. At the copper electrode, hydrogen ions present in the acidic solution gain electrons and form hydrogen gas. This tiny chemical reaction is effectively converting chemical potential energy directly into electrical energy. In other words, every lemon battery is a microscale power plant performing electrochemical energy conversion in real time. The efficiency of this process depends heavily on factors most people never consider. The purity of the metals, the distance between electrodes, the concentration of ions in the electrolyte, and even the temperature of the environment all influence how effectively electrons move through the system. Warmer conditions accelerate chemical reactions, increasing current output slightly. Higher acidity improves conductivity. Even the surface area of the electrodes matters, because larger contact areas allow more reactions to occur simultaneously. These details matter because they reveal an uncomfortable truth about emergency engineering. Survival technologies rarely fail because the science is wrong. They fail because the practical details are misunderstood or ignored. A poorly constructed lemon battery might produce almost no electricity at all, reinforcing the misconception that the concept itself is useless. But a carefully designed array using optimized electrode placement and conductive wiring can produce dramatically better results. And this brings us to the larger survival lesson hidden inside something as simple as a lemon. In a world dependent on massive energy infrastructures, people often forget that electricity is fundamentally a chemical phenomenon accessible with minimal resources. The modern grid merely scales this phenomenon to enormous levels using turbines, generators, and industrial systems. But the underlying physics remains the same whether electrons are pushed by a spinning generator in a hydroelectric dam or by zinc dissolving slowly inside a piece of fruit. The danger arises when society forgets these principles entirely. When the grid fails, most people assume electricity simply disappears from the world. In reality, the potential for electricity remains everywhere around us. Locked inside chemical gradients, temperature differences, and mechanical motion. The challenge is not the absence of energy, but the absence of knowledge about how to convert it. The lemon battery is a reminder that the first step toward restoring power after a disaster may not involve rebuilding massive infrastructure. It may begin with rediscovering the smallest and most primitive forms of electricity generation. And once that door opens, it leads to a much larger and more powerful realization about energy, chemistry, and survival engineering that few people ever consider until the lights go out. When electricity disappears from daily life, the psychological effect is immediate and severe. People instinctively interpret darkness and silent machines as the complete absence of energy, as if power itself has vanished from the physical world. Yet this perception is deeply misleading. Energy has not disappeared at all. It remains present in chemical bonds, temperature gradients, mechanical forces, and electromagnetic fields that exist everywhere around us. The true crisis during a grid failure is not the disappearance of energy, but the collapse of the systems designed to convert that energy into usable electrical form. The lemon battery illustrates this distinction with unsettling clarity, because it proves that even in the most primitive conditions, electricity can still be produced using materials that most people would never recognize as components of a power source. To understand why this matters, it is necessary to examine the deeper electrochemical mechanics occurring inside that seemingly simple citrus cell. When zinc is inserted into the acidic environment of the lemon, atoms on its surface begin to oxidize. Each zinc atom releases 2 electrons and becomes a positively charged zinc ion that dissolves into the surrounding electrolyte. These electrons cannot remain inside the metal without creating an electrical imbalance, so they begin migrating through the external circuit connected to the copper electrode. This movement of electrons is what we recognize as electrical current. Meanwhile, inside the electrolyte, hydrogen ions from the citric acid migrate toward the copper electrode, where they accept those incoming electrons, forming hydrogen gas in a reduction reaction. The system continues operating as long as the chemical gradient between zinc and copper remains strong enough to drive electron movement. This explanation reveals a critical misunderstanding that often surrounds small electrochemical power sources. Many people assume that the electricity stops quickly because the fruit runs out of power. In reality, the limiting factor is usually the deterioration of the metal electrodes rather than the depletion of the electrolyte. Zinc gradually dissolves during oxidation, weakening the electrode and reducing the efficiency of the reaction. Meanwhile, hydrogen gas can accumulate on the copper surface, creating a barrier that interferes with further electron transfer. This phenomenon, known as electrode polarization, was a major challenge for early battery designers during the 19th century and forced engineers to invent methods for removing or neutralizing these gas bubbles to maintain consistent current flow. One of the earliest solutions to this problem emerged during the rapid expansion of telegraph networks across Europe and North America. Engineers required batteries capable of delivering stable electricity for months at a time without interruption. The lemon-style electrochemical reaction was already understood, but it was unreliable in its simplest form. This challenge led to the development of improved electrochemical cells such as the Daniell cell, invented by the British chemist John Frederick Daniell in 1836. Daniell's design separated the copper and zinc reactions into different compartments connected by a porous barrier, preventing hydrogen buildup and dramatically increasing stability. For decades, this battery design powered telegraph systems that carried the first long-distance electronic communications across continents. The lesson hidden within this history is profoundly relevant to survival scenarios. Primitive energy systems often appear unreliable only because their chemistry is poorly managed. When the reactions are stabilized and optimized, even extremely simple electrochemical cells can produce surprisingly consistent power. The lemon battery represents the most basic version of a galvanic cell, but the same principles can be expanded and improved with small adjustments that dramatically increase performance. Consider the role of the electrolyte. The citric acid inside a lemon provides conductivity by allowing ions to move freely between electrodes. However, citric acid is not the most conductive electrolyte available in natural environments. Saltwater solutions often perform better because dissolved sodium and chloride ions increase electrical conductivity significantly. Vinegar, which contains acetic acid, can also function as a strong electrolyte. Even soil saturated with mineral-rich water can serve as a crude electrochemical medium. In survival conditions where citrus fruit may not be available, understanding this principle allows a person to construct similar cells using materials found in nature or abandoned infrastructure. The metals themselves are equally important. The voltage produced by a galvanic cell depends on the difference in electrochemical potential between the two metals involved. Zinc and copper happen to produce a convenient voltage difference of roughly 1 volt, but many other combinations exist. Magnesium paired with copper produces a higher voltage because magnesium releases electrons even more readily than zinc. Aluminum can function similarly under certain conditions. Iron, though less reactive, can still participate in electrochemical reactions when paired with more noble metals. These combinations are governed by what chemists call the electrochemical series, a ranking of metals based on their tendency to lose electrons. The existence of this series means that electricity generation does not depend on any specific material like lemons or copper coins. It depends on differences in chemical behavior between metals and the presence of an electrolyte capable of transporting ions. This realization dramatically expands the number of potential power sources available in a survival situation. Scraps of metal from destroyed vehicles, wiring from damaged buildings, and even corroded hardware can be repurposed into functioning electrochemical cells when placed into conductive environments. Evidence supporting this adaptability appears in numerous field experiments conducted by survival researchers and emergency preparedness specialists. Improvised batteries constructed from aluminum cans, steel nails, copper wiring, and saltwater-soaked cloth have successfully powered small radios and LED lights in controlled demonstrations. These systems remain inefficient compared to modern batteries, but efficiency is not always the primary objective in emergency scenarios. Reliability and availability become far more important than performance metrics. However, there is another misunderstood factor that determines whether primitive electrochemical power sources can become genuinely useful: energy storage. A lemon battery produces electricity slowly and continuously as long as the chemical reaction persists. Many devices, however, require brief bursts of higher power rather than constant microcurrents. This mismatch can be solved using capacitors, components capable of storing electrical charge over time and releasing it quickly when needed. By connecting a small electrochemical array to a capacitor, even a weak current can gradually accumulate energy until enough charge exists to power a device momentarily. This principle has enormous implications for survival technology. Imagine a scenario in which a radio transmitter requires only a few seconds of power to send a distress signal. A lemon battery array connected to a capacitor could slowly charge that capacitor over several minutes or hours. Once the voltage reaches the necessary threshold, the stored energy could be discharged instantly to transmit the signal. In this way, a seemingly insignificant power source becomes capable of supporting intermittent communication, one of the most critical requirements during disaster recovery. But perhaps the most important insight emerges when examining how scalable these electrochemical systems truly are. Most demonstrations use only a handful of lemons connected with short wires. Yet there is no theoretical limit to the number of cells that can be combined in an array. Hundreds or even thousands of small galvanic cells could be assembled if materials were available. Each additional cell contributes more voltage or current to the overall system depending on how the connections are arranged. In large enough numbers, even primitive cells can begin producing meaningful levels of electrical power. This scaling principle mirrors the architecture of modern battery packs used in electric vehicles and grid storage systems. Those enormous energy banks are not single massive batteries but networks of thousands of smaller electrochemical cells arranged carefully to achieve desired electrical characteristics. The same logic applies whether the cells are advanced lithium-ion modules or improvised fruit batteries assembled on a kitchen table. The danger arises when people underestimate how quickly electrochemical reactions degrade without maintenance. Electrodes corrode, electrolytes dry out, and chemical gradients weaken over time. Without periodic replacement of components, the electrical output gradually declines until the system fails entirely. This reality highlights another overlooked aspect of survival engineering: sustainability. A power source that cannot be maintained with locally available materials is only a temporary solution. In the case of lemon batteries, the limiting resources are the metals rather than the fruit itself. Zinc electrodes dissolve gradually during operation, meaning they must eventually be replaced. Copper remains more stable but can become coated with reaction byproducts that reduce efficiency. Over extended periods, maintaining a functioning electrochemical array would require scavenging and recycling metal components continuously. Yet even with these limitations, the core principle remains powerful. Electricity generation is not restricted to industrial power plants or complex technology. It can emerge from simple chemical interactions occurring in environments as ordinary as a piece of fruit or a container of salt water. When the infrastructure of civilization collapses, the individuals who understand these interactions gain a small but significant advantage. They possess the knowledge required to produce electricity when most people believe it is impossible. And once that understanding takes hold, a deeper question begins to surface, one that pushes beyond lemons, metals, and improvised batteries. If electricity can be extracted from such simple chemical systems, then how many other hidden energy sources exist in the everyday world around us, quietly waiting to be converted into power by those who know where to look?